the 23rd webinar of ACigs webinar series. Today is 18th of August 2021 here in Brisbane, Australia, and we have a very interesting webinar today with Amir and Amar, both from Global Synthetics. The webinar today is, as I said, the 23rd webinar of the series that Australasian chapter of the International Geosynthetic Society has been broadcasting in the past 2 years. So welcome to this webinar. As you know, IGS is a global society with more than 45 chapters, and Australasian chapter is where we are at. Basically, we cover Australia, New Zealand, and Pacific Islands. This is the website of the IGS, the International Geosynthetic Society. So the address is geosyntheticsociety.org. Also, we have our up-to-date ACigs website, as you can see, and I definitely encourage everyone again to visit our website. The address is ACigs.org, ACIGS.org, and you will see all of the upcoming events, all of the information about the memberships, the news, the bulletins, and technical resources, all available on the website. As part of the website, we also have all of the recordings of the previous webinars that we've had, as well as lectures and seminars that we had recorded. So everything is available from our website, again, under the technical resources page. At the end of this webinar, if you require a certificate of attendance, we can definitely organize that for you. Please email info@acigs.org, and then we can arrange the certificate to be sent to your email address. Today's webinar, we thank our sponsor for this event, Global Synthetics. They are the sponsor of this event today. So thank you to Global Synthetics for their sponsorship of this webinar today. And the topic of the webinar is considerations for design and modeling of geogrids for soil stabilization and reinforcements. And this will be presented by Amir Shahkolahi. So a brief bio from Amir. I just have to move my screen a little bit, sorry. Amir has a bachelor's and master's degree in civil engineering. As a designer, project manager, and researcher, he has been involved in civil and geosynthetics industry over the last 20 years. He's a technical manager at Global Synthetics. Amir is the vice chair of the Australian Geomechanics Society, AGS, Queensland chapter, member of the International Geosynthetics Society Technical Committee on Reinforcement, TCR, also Stabilisation, TCS, and board member of American Society of Civil Engineers, ASCE. Australian section, then member of the ASTM Committee, D35, on Geosynthetics. Industry board member of the Australian Pavement Research Hub, board member of ARC Training Centre for Advanced Technologies in Rail Track Infrastructure, ITTC, Rail, and member of the Standard Australia Technical Committee CE032, Reinforced Field Structure Working Group. He is also a board member of the International Geosynthetic Society Technical Committee for Barriers, TCB, board member of the Queensland Landfill Working Group, board member of the Waste Management and Resource Recovery Australia in Queensland, and guest lecturer at Sunshine Coast University and University of Wollongong. And the industry supervisor and advisor for several geosynthetics research projects in Australia and overseas. So thank you, and this was my intro slides. I stop share from my end, and Amir, all yours for your presentation. Thank you.
Okay, thank you, Siomek, for your nice introduction and for your kind introduction. Thank you, ACigs, for this opportunity and for providing us with this opportunity to present. And also thank you everyone who is attending the presentation today. As Siamak mentioned, it is presentation today. It is about considerations for designing and modeling geogrids for soil stabilization and reinforcement. It's a pleasure to be with you guys, and I will start with going into straight away to the main topic. We all know about mechanistic empirical design. So this presentation, I assume that we know the basics. I may go through the basics just very briefly, but I'm not going deeply into the basics, just short introduction to basics so we can all be on the same page. In mechanistic empirical design, we have the first part, which is the material and climate and traffic data going to a structure. We assume a structure, and this structure, then we go to the response model and take the response, and then we go to damage models and then calibrate the model that we have, and this becomes the mechanistic empirical model. Now, the question is always, how should we use geogrid in mechanistic empirical design? There are several ways to do that, and there are several ME design programs available at the moment. Step one is checking the benefit and proving the concept of geogrid. First of all, we should check the concept in the lab and see if it works and what does it do, and then we go further. To do that, the first question we should answer and we should think about is, why do we want to use geogrid? What performance or benefit we are expecting from geogrid? This is the main point. And then we go to the next question, which is now, how should we prove or study the performance of geogrid? When we answer these questions, we can check the performance. And actually, the presentation today is mainly focused on answering these two questions. Then we have step two, which is validating the through full-scale pavement test, like APT. And then step three is the field performance monitoring and calibration. Now, let's focus on these two questions. Question number one. So actually, question number one tells us, why do we need to use geogrid? There are just some examples. It can be less or more. Do we want a longer design life, less thickness? We want less surface deformation or rotting? Do we want less cracks in the asphalt layer? Do we want less ballast breakage or less track deformation if it's a rail, for example? Are we improving the bearing capacity of subgrade? Less subgrade deformation, reducing the thickness of the subgrade replacement, and many more. It is very important to first know what we want to test or what we want to achieve, because each benefit that we see here, they can be achieved through different mechanisms or functions. By knowing that, then we can go to the next question, that how should we study geogrid? We should know what needs to be checked, where should I put the geogrid, what parameters will affect the performance, what tests should be done, how can test results be used in the design. So these are some of the questions that come to our mind when we want to study geogrid. Now, how to answer these questions? There are several steps to study or prove the performance, which is the first step of mechanistic empirical design. To do that, to prove or study the performance of geogrid, the first thing is to understand the application, which is relevant to the performance and objective. So we first know what we want to achieve. Now we should see which application is relevant and related to our objective and performance that we want to achieve. Then what is the function that is applicable to that application? Then after that, what's the mechanism for that specific application? Then we should understand what are the relevant properties of the geogrid that can affect and are related to that function and mechanism. And after that, we can determine the performance criteria, and then we should select the right test and the right model to check the performance criteria. This test and this model should be able to use the mechanisms and consider the effect of relevant properties to provide the function to achieve the objective. So it's combining all the four steps above. Then we should analyze the test results based on all parameters. I called it integrated analysis. So we should consider all the effective or the parameters which affect the design, and then consider all of them in our analysis, and then apply that to the model. This slide is actually our main slide today, and it's the main thing that we will focus, and we go through each of these 7 steps in this presentation today, and this is what we discuss. Now, if I want to put it in a flowchart for you to have a better understanding, this is how it looks like, what we discussed so far. So when we know what is the reason we want to use, what's the benefit or performance we want to achieve, Next step is how to study and check the performance, which has different sections, as you can see, to understand the application, function, mechanism, properties, and then criteria. Then we go to a test model and test, write test and model, and then analyze and then use it in the design. Let's go to this section with more details to study each of these parameters separately. Now, this section, performance, applications, functions, properties. Where does mechanisms stay? The mechanism is actually the way to connect the application to function. This is how GeoGrid works. So the performance, why we use GeoGrid, then we go to what GeoGrid needs to do, and through how GeoGrid works, we get into the functions. And then based on that, we can get the relevant properties. Let's start with applications. Some of the applications, stabilization of unbound aggregate, it can be road-based, sub-based, ballast, sub-ballast, stabilization of soft soil, controlling cracks due to swelling subgrade, controlling reflecting cracks on asphalt overlay, increasing fatigue life of asphalt, reinforced slope and walls, basal reinforcement, load transfer platforms. Of course, this presentation today, we don't have to go through all of it. So we focus on mainly roads and railway applications in this presentation today. Next one is the functions. So the functions these are the main functions, let's say, in infrastructure. Separation, filtration, reinforcement, stiffening or stabilization, doesn't matter what we call it, different people or different references call it different, but the concept is the same here. Drainage, protection, barrier. See some of the definitions in the market about reinforcement and stabilization. Reinforcement, according to Zorenberg, Dr. Zorenberg, is development of tensile forces to actually in the geosynthetic material to maintain or improve the stability and bearing capacity of the soil geosynthetic composite. And the key parameter here is the tensile strength and stiffness. According to ISO definition for reinforcement, it is the use of a stress-strain behavior of a geosynthetic material to improve the mechanical properties of soil or other construction materials. And stiffening, according to Dr. Zorenberg, is development of tensile forces in the geosynthetic material to control deformations in the soil geosynthetic composite. The main design parameter here is soil geosynthetic composite stiffness. And according to ISO, stabilization improvement of the mechanical behavior of an unbound granular material by including one or more geosynthetic layers, such that deformation under applied loads is reduced by minimizing movements of the unbound granular material. So we are not here to talk about definitions. We are accepting the definitions that are available in the market, and we just focus on functions and applications and what we need to achieve. Now, where should we use GeoGrid? It actually depends on the functions that we want to achieve or we want to study. As we all know, this is a famous graph by Dr. Zorenberg. The reinforcement, mainly geogrids we are talking about here, can be on top of subgrade, between subgrade and subbase, or it can be under the asphalt. These are the reinforcement sections that we get. If you want a stabilization or stiffening, whatever we call it, then we can have it again between subbase and subgrade, or within the base material, or between subbase and base or asphalt. So if you can see here, this location is same benefits and stabilization. So, but depending on the application, we can get either stabilization, reinforcement, or both, depends on what we want to do. And sometimes we put all together to get all the benefits at the same time. So it all depends on the functions that we want to achieve, and it gives us the location that we would like to use GeoGrid. Now, next one, that we understood the application, and then based on application, the function, and now let's see what's the mechanisms that can help us. So we all know about mechanisms of GeoGrid in road and railway. The main mechanism of GeoGrid, regardless of the type of GeoGrid, is lateral confinement. So lateral confinement is the main parameter, is the main mechanism that we get with GeoGrids, and it is very simple based on interlocking and friction. Depending on the GeoGrid, we have lateral confinement in the particles, and then it controls the lateral movements of the gravel. That's why we achieve less deformation and all the other benefits, which we can see in the next slide. So because of lateral confinement, according to Dr. Steve Perkins, we have 4 components for that. Lateral, the strain, of the aggregate. So we don't have, we reduce the movements, lateral movements of the aggregate because of this lateral confinement effect. We increase the lateral stress in the aggregate, which can end up with higher combined modulus. These two effects are the effect of geogrid on the granular material. At the same time, we have geogrid at the same time have some benefits for the subgrade, which is reducing vertical stress on the subgrade and reducing shear stress on the subgrade. So as you can see in the graph here, benefit 1 and benefit 2 are for geogrid, are for gravel layer, and benefit 3 and benefit 4 are for subgrade, if we put geogrid between subgrade and gravel. Now, this graph from Dr. Zoremek shows it very well, that when we have without geogrid, which is section A, the gravel is trying to spread. With geogrid in section B, we have lateral confinement in the gravel. Again, section A, you can see this higher normal force going to the subgrade, while section B is less because of wider load distribution angle. Now, the second potential mechanism is bearing capacity increase. And it's very simple that we are going away from punching shear to general shear by using geogrids. And then we have tension membrane. Tension membrane is actually when we have high rotting, more than 75 to 100 millimeter rotting depth, then geosynthetic becomes into a concave shape and it supports the wheel. And to consider the effect of tension membrane, you can see we have P and P star. Actually, Giroud and Ray studied this in 1981, and it's very simple. It is actually the stress, the normal stress on top of the geosynthetic, mainly geotextile, is P, and then the actual stress on the subgrade is P star, which is P minus PG. PG is that tension membrane, which is calculated by this. So this is how we consider tension membrane. But as I said, it's mainly for rotting is more than 75 to 100 millimeter. Now, what is the zone of influence of geogrid? The zone of influence of geogrid, there are several studies. I just summarized some of them here, that most of the studies in the world, they conclude that it's between 100 to 150 millimeter on both sides of the geogrid. So you can see on the left-hand side, the study by Steve Perkins using an RTL test, which is a repeated triaxial load test. And then you can see in the right-hand side, a study by Warwick in 2018 and Dr. Tutumbrul et al. That they conclude this nice graph, fully confined 100 to 150, partially confined 100 to 150, and what we call unconfined, which is actually not 100% unconfined. There's still some confinement, but anyway, let's call it unconfined. And other similar studies, as you can see on the slide, have got the same results. Now, after the mechanism, next thing is the properties. Now, what are the properties? Geogrid properties are different. We can have ultimate tensile capacity of the geogrid, stiffness, which is the tensile capacity at 0.5 to 2%, sole geogrid interaction, sole geogrid composite coefficient or stiffness, junction, which can be junction strength or junction stiffness, which was introduced by Eli and Steve Perkins, or roughness and survivability and long-term performance. So not all of them will contribute to all the mechanisms, all the functions. It's just a list of the properties that are meant for geogrid. Based on, we are going through all of these because we don't know. But one of the main and the keepers that can affect the modeling is this only in this presentation because of time. This is the thing that can directly affect the performance. And let's see. Sole geogrid interaction is a combined effect of geogrid type, rib properties, including the thickness, width, the surface of the rib, aperture properties, the ratio between aperture size to gravel size, rib stiffness, soil density. So it's a combined effect. Not single parameter can affect just without considering others. So it's very important to know that when we are studying the sole geosynthetic interaction, it is not because of only one of these parameters. For example, this is a pull-out test, and it shows very nicely by Joel that how this works. This is the geogrid in pull-out test. As you can see on top right-hand side, it shows the forces. So there are three main mechanisms. For example, when we have pull-out tests, that shows the interaction between geogrid and gravel. It can be bearing resistance of the geogrid ribs. It can be resistance due to rotation of the transverse ribs, and it can be surface friction on longitudinal and transverse ribs, as you can see. So all of them, some of them less, some of them more, depending on the geogrid, can be involved, and this can provide the interaction for us. This is very important, and all of them, less or more, can be involved. Now, I like this graph. It's nicely described by Moblick and his team actually in 2018. This graph, it's pull-out test on many different geogrids, different types. And as you can see, this graph shows that the interaction intensity is actually depending on the friction, which is the black soil, then interlocking, then we have the influence of geogrid type, divided by D50, which is the ratio between opening and gravel site. So this graph shows nicely that all these parameters are involved in the soil geogrid interaction. Now, again, we don't have time to go through all of this, but one of the main things that we see that, okay, it's very easy to consider the effect of friction or soil type, because soil type is same, we can find same soil type. But what is sometimes let's say confusing or misleading is that the type of geogrid. Now, different types of geogrid, as you can see in this graph, it is a range. So there's a range for type of geogrid. It means different types of geogrid can interact with gravel in a different way, different mechanisms between these three that we discussed. And the reason we want to discuss this is it's very important. If we develop a model for one type of geogrid or one type of soil or interaction between geogrid and soil, we cannot necessarily apply it directly to all other geogrid types. Now, depending on the effect of, let's see what is the effect of effect of geogrid type. We normally have welded geogrid, extruded geogrid, and then we have woven geogrids or flexible geogrids. When we have extruded geogrids, the friction between soil and ribs still exists. It is a little less because they are smooth surface, depending on the surface. Bearing resistance is one of the main mechanisms in front of the ribs, and thickness plays a role here. With flexible geogrid, it's mainly friction. With welded geogrid, friction is higher because of the ribs, if the ribs are friction. The bearing resistance in front of the ribs exists, but the thickness is less compared to other grids. And then resistance due to rotational transverses. So it doesn't give any idea of which product is better than the other. This is not a true statement to say. It's just different products, different mechanisms. You can have a study that all of them perform the same. At the end, the performance is the same. There can be one test that one of them performed better than the other, and you change the test and the other one performed better than the other one. So it's not about which one is better, which one is not better. It's just going through different mechanisms. Now, for extruded geogrids, as you can see, this photo shows nicely how this bearing resistance in front of the rib can act and can help. This is actually the photo after the pull-out test, and you can see the ribs are bending. And the thickness of geogrid is, the ribs are very important here. So different geogrids with different thicknesses of the ribs can perform differently, even if everything else is the same. Now, this is what we see, for example, in the pull-out test. This is the image that they got many years ago, and it shows the interaction. As you can see, in front of the ribs, it is a passive area, and then an active area, and then a passive area on the other side. So it is very well shown here. And then on the right-hand side, you can see how stresses are applying on a rib. It's the cross-section of the rib. Now, many years ago, in 1989, actually, they developed a chart that shows a range for this normal stress in front of the rib, depending on the normal stress on top of the rib, which is sigma n. So sigma p is the stress that faces the rib, and sigma n is the normal stress on top of the geogrid. And you can see there is a range. The lower range, the lower limit, is based on the punching failure of the foundation. So this mechanism that you can see, that's how they developed that equation for sigma p to sigma n. The upper limit is now taking into account the characteristic stress field under a low laying foundation without punching through. So this is the equation on the top. This was developed some years ago, many years ago, and this shows the range based on different studies. Now, thickness is very important here, as you can see, and then based on that, we can calculate the force. P is actually the force which is applying to that rib, and then T is the tensile resistance. F1 and F2 are the factors. F1 is the scale factor, which is the empirical factor for ratio of rib thickness and D50 of the gravel. And F2 is the empirical factor for the shape of the rib. And this is how we calculate, or suggested to calculate, the PQ and the T, which is the transverse tensile resistance for porous log, punch and drown, or extruded geogrids. And this is a very nice, important equation. Now, thickness is important here again. As you can see, they provided another graph which shows the effect of thickness. If you look at this, B is the thickness of the rib and S is the aperture size. And again, there is a range, lower range and upper range, A and B, versus it's for the S divided by B to give fully rough bond. So as you can see, again, thickness plays a role, and of course, horizontal is the phi of the gravel or the soil. Something interesting that could be found, for example, in one of the tests by Mishra at Illinois and Dr. Errol and his team, it is a large scale track cell testing, and then they develop a DEA modeling based on that. And as you can see, they use the punch and drawn here, geogrid. And you can see the dots, black dots are the laboratory measures, and the white one was a DEM model that was developed based on that. Just the thickness of the ribs are, sorry, the DEM is the black triangle, sorry, the white triangle is a lab test. And the ribs in the DEM model, it was increased, the thickness was increased by 10%, and you can see the difference between the results. Now, we know how to study extruded geogrids now, and what are the important parameters when we want to develop a model. It can be DEM modeling, finite element modeling, or any model. These are the considerations. For welded geogrid, as you can see, after the pull-out test, welded geogrid looks like that. And then this, you can see the resistance due to rotation of the cross elements. Now, how to take into consideration, Ziegler and Turner in 2003 made some calculations and modeling, and based on pull-out test. And as you can see, this is what they developed. And tau shows the force. And then based on that, this is mob L, which is actually the length that is activated, that tau is activated. And then they said that this mob, and you can see in the bottom, that equation is how we can calculate that mobilized length. And then you can see on the right-hand side, it shows the effective area. Of course, the distance between the cross ribs always affects that length, of course, as you can see. And you can see that curve shows the passive and active area in front of the ribs and in the back of the ribs. Now, based on that, they also suggested graph and for calculating the mobilized length. You saw the equation in previous slide. And based on that, this is the suggested equation for tensile resistance. So it's a little different to the other geogrids. So it's again, different geogrids, different interaction. It's all to say there are different geogrids are different, and we may need to use different equations or parameters and interactions in our modeling. Now, let's go to the next one, which is the ratio between aperture size and soil particle size. This is very important. Look at this study by Molbeck and his team in 2018, that it shows very nicely. The vertical axis is P, which is the pull-out test resistance, and then the horizontal is S divided by D50, and it clearly shows, depending on the size of the gravel, the graph is different. So it clearly shows the effect of gravel, which can affect the amount of interlocking. Similar results was, similar concept, let's say, was reported by Rokin and Jewell. It is a shear test, direct shear test. And as you can see, there are three zones here. The vertical axis is the composite coefficient, and the vertical is DO, which is the opening size, divided by D50. If we are in a like zone 1, in zone 1, you can see that the opening is very high. So it's a large opening, and the particles are very small. So this shows that the shear failure will be on top of the ribs. And there is still some friction between the gravel inside the aperture and the gravel on top. If we move to section 2, area 2, which now we have good interlocking, because in section 1, the gravels it's very large aperture. So in section 2, the gravel can go into the aperture and we have some good interaction and interlocking. So you can see in area 2, actually we have some confinement in the gravel directly on top of inside the aperture and on top. So we have some interaction here, and then we have friction between that gravel and upper layer. That's why the shear failure is pushing up, not directly on top of the ribs. Again, when we go to the lower end, which we have a very large particle size, we miss the chance of interlocking again, and the shearing failure can be pushed again on top of the gravel. Now, another set of tests was reported by Rokin in 2013. They did check the effect of aperture size using D50 and D90 both. And they realized that D90 can be a better indicator to study this, let's say, this mechanism. What is the other effect? Another effect of aperture size, apart from the interaction that we discussed, is actually what is called interference or mutual influence. As you can see, right-hand side, you can see there are many ribs. It means the spacing is low. The left-hand side, there are only 2. So you can see in the right-hand side, there's an overlap or mutual influence of the ribs. This was studied very nicely by Palmeria in 2009. And this is the graph. DI vertical axis is the degree of interference, and it's calculated, as you can see. P is the pull-out force, and P0 is on only one rib. And then based on S and B, they gave this graph. So it's very interesting. With this graph, they say that if the S divided by B is more than 40, you actually miss the DI, so degree of interface. Before that, you can see it's for different square and round membrane or members, and then for different number of ribs. This was also studied by some other people, as you can see. And you remember we talked about this P force. This is a very interesting graph. If you look at it, P versus sigma n, on top circle, the 2 circles, you can see the phi for the soil is the same, but the number of the ribs are more for the circle in the bottom, and it shows the effect on PQ. This graph also shows the effect of phi as well, because if we have same number of ribs, but the phi value is less, you can see the graph goes underneath the blue one, so goes down. Now, what is the soil geogrid composite coefficient? Soil geogrid composite coefficient is actually the ratio of composite strength between geogrid and soil to the shear strength of the soil. This is the equation that is suggested in references, and there are parameters. We are not going into the details what it do. It's just to show you what it is and what is available, and for non-cohesive soil as well. And they suggest it's less than 1. This is important parameter. We don't have time to go through all the details, but it is very, very important because a lot of applications, especially for stabilization and stiffening, this is what is very important. Now, Dr. Zornberg introduced a new parameter, which is coefficient of combined or composite soil and geogrid stiffness. He developed this is the model based on pull-out test, and these are the functions that is used in that model. As you can see, J, C here. So this is what was suggested by Dr. Zornberg as the unit tension at location X is actually relevant to K, which is the stiffness of the soil geosynthetic composite, the value and the parameter that was introduced. And Ux is the displacement. So it means that the graph looks like this. It's the slope of that graph. And this is how Kg is calculated. 4 times tau y multiplied by j, and j you can see is from the top graph. So again, we don't have time to go through the details what it is, but this is what is available. There are references available that you can refer to and study full about this very interesting parameter, I would say. Now, 5th one is now, let's select the right test and right model. There are different tests available. We have a small scale laboratory tests like track cell test, directional test, plot test, CBR test. We have medium to large scale lab tests, like again, large scale track cell test or direct shear test, large one, large plate load test, or we have full scale pavements like APT, which is in the controlled area, and we have full scale field trials, which is uncontrolled area. Now, again, field trials can have controlled conditions for construction. Of course, you cannot control the, let's say, the climate, but some of the parameters you can control, or you can use some of the roads which is already being built. So there are different test methods, and all of them, they have some benefits and some limitations. Which test method we should use? It very depends on what we want to study. Do we want to study the overall performance and benefit of the geogrid, general approach? Okay, we can use it. For example, do we want to test the traffic benefit ratio or base cost reduction or settlement? Okay, we can use, for example, plate load test, full scale fit trial, or APT. Or are we testing the mechanisms and property? This is very important step. Sometimes there's a confusion. We don't know which test to use, or we mix the tests and we don't know what we want to get. So you should first determine what we want to test, the performance, overall performance, or the mechanisms, or the effect of properties. For example, do we want to test the increase in the modulus? Or do we want to test the shear properties? Do we want to test the deformation of geogrid or reinforced aggregate, or the stress reduction, or deformation of the subgrid? So we should know what we want to test. And of course, the limitation of each test should be considered. For example, these are some of the limitations of the tests. Small scale lab test, the scale effect can be a problem. It does not model the total performance. It's good to check the properties and mechanisms. May not be able to test all properties, of course. Results cannot be used directly in the design. It is not representative of the field condition and may not be able to consider all geogrid soil interaction mechanisms. What about medium to large scale RAP tests? For example, plate load testing in the lab, as an example, or large scale track cell testing. It is not representative of field and actual load. It's good, but it's not exactly actual conditions on the site. Results cannot be used in the design. That's very important. It is not a design test. Whatever we get in the design, traffic benefit ratio, base cost reduction, this is not a design value. It's a very good value, but it needs to be calibrated to be able to be considered as a design value. So it's good to study the mechanism and performance comparison. Field test, if it is full scale field test, it's good, but there are lots of uncontrolled conditions, so we should make sure that we control as many as parameters that we can. And if you change the testing condition, maybe the results may change. Just to give an example, we all know that we use track cell testing, repeated load track cell testing, to determine the modulus. This is a very typical way of determining the modulus. And as you can see in this graph, we have plastic strain and we have resilient strain. And we use resilient strain to calculate the resilient modulus. This is a very typical approach. Now, let's go through an example. The study in 2012 with no geogrid, one geogrid, two geogrids. This is the resilient modulus that they got for unreinforced versus reinforced. Abu Farsakh and his team. The results did not show significant change in the resilient modulus with geogrid. This is opposite to what we expect. Same result was achieved by some other researchers, that they didn't see benefit in resilient modulus by using track cell test. So what is wrong? Is geogrid not providing resilient modulus, or we are doing something wrong? We can see the answer in this slide. This is, as we said, how we measure the resilient modulus. Now, the point is, when we use geogrid, we reduce the plastic strain, but we don't reduce the resilient strain. Look at this graph. It is, again, output of the same test. The resilient strain for reinforced and unreinforced are almost the same. That is why we didn't see the benefit in resilient modulus. So the plastic deformation is less with geogrid, but the resilient modulus is not. And that is why the modulus is good. So it means that the track cell test is not a good test to see the effect of geogrid in resilient modulus. We should use another tests. And the main reason is resilient strain is perpendicular to geosynthetic orientation. So geosynthetic cannot provide any vertical restraint during rebound. That's the main reason that we cannot use track cell test to study the effect of geogrid on resilient modulus. There are some other methods instead. For example, Errol and his team, they introduced the Binder element, which is a very nice method. There are some cyclic shear box test or cyclic pull-out test introduced by some other research like Bing and Han and Coelho and his team. But these two tests, they said what the outcome is resilient interface shear modulus. Test method can affect the result, yes. So it's very important which test method we use. And if we change the test method, we get the different results. You may have seen this slide before in my presentations. This is just an example. Different test methods to check the optimum geogrid aperture for ballast. Different test methods give different optimum results. Even the first three, the geogrid is the same, but the test method is different. So it's important which test method we use. And what test method we should use? A reasonable test method is the one that can have the ability to capture the mechanism of the lateral strain, provide parameters that are suitable for ME design, provide good repeatability of test results, that utilize parameters that distinguish between the performance of different geosynthetics, be sensitive on the low displacement, and be easy to conduct, and can show all the benefits that we like. Models that we can use, it can be finite element models, or it can be DEM models, different models. But what is very important to consider is that mainly these models are based on and are calibrated or developed based on a particular test method, like pull-out or direct shear. So the limitations of those test methods should be considered and can affect our model. Now we should know, is the model that we are developing, is it capturing all the effective parameters for soil geogrid interaction that we discussed? This is one of the main important things to have a model. Can the model which is calibrated for one geogrid be used directly for other geogrids? May not. It may be necessary to calibrate that one for all other geogrids. Now that we know the interaction mechanisms can be different. Example, as an example, DEM modeling can be based on triaxial tests, for example, by Mishra and Errol and his team, can be based on pull-out tests, can be based on direct shear tests, and as you can see, there are DEM modeling, but each of them are studying a different mechanism or different parameter. Another example of effect of geogrid type in the modeling, for example, this is in finite element modeling that was developed by Ziegler in 2016 and his team. There are two different geogrids, welded geogrid versus extruded geogrid. It is the junction. And this is how they could model the junction in finite element. And this is the strain in the junction. And as you can see, the strain and the behavior of junctions and the ribs and how the load is transferred are completely different. So if we want to model the geogrid, we may need two different models for two different geogrids or three different geogrids. This slide, I like it, clearly shows that there are differences. Now, to analyze the test results based on all parameters, integrated analysis. I go back to my slide that says soil geosynthetic interaction is a combined effect of all these parameters. That is why when we do a test or make a model, we should analyze the data considering all these parameters, not only one or two or three parameters, because all of them are working together to give us a performance. The only way to see the effect of only one single parameter is if we can keep everything else completely the same, which is most of the times very difficult. The results for a test may not be directly applicable to other geogrids or soil with different parameters as listed above. If we test different geogrids that few or all the above parameters are different, then we can not only conclude on one or two parameters. This is something interesting in the last point, that the effectiveness of the geogrid properties can be different for different gravel depths, rock depths, or geogrid mechanisms. So if we change the thickness of the gravel, we may see that some parameters are less effective or more effective now that we have changed the gravel with the same geogrid. So the thickness of the gravel, as well as the amount of rotting, can change the interaction and effectiveness of property. Look at this nice outcome. It is from Eli Coelho and Steve Perkins' full-scale trial that they did in 2014 at Montana State University. These are the parameters that they concluded to be effective parameters that are listed on the board, let's say, that you can see. Now, phase one, they used 200 millimeter gravel in the full-scale field trial. Phase two, they used 277 millimeter of gravel in the full-scale trial. Two different gravel. As you can see, there are two different graphs, and the vertical, which is the R square value, for each parameter is a little different for different gravel depths. Now, as you can see, also the routing is different. So for different routings, 25, 50, 76, or 100, the effectiveness of each parameter is now different. So this clearly shows the amount of routing and also the amount of gravel thickness can affect the effectiveness of each property in the performance. Now, the last is how to apply test results to design. Go back to this slide. ME pavement design, mechanistic, empirical. It has a mechanistic part and an empirical part. Mechanistic part is mainly the response part, for example, a finite element model, and empirical part is through the damage and transfer equations. Now, we have two ways to consider geogrid in the ME design. It's a modification in the material properties, for example, the modulus, like what AASHTO does, or modification in the transfer function that incorporates geosynthetic benefit. So one of these two ways or both can be used. This is a nice slide, that I used. This slide, this shows, for example, it's a response model, that a finite element model. These are the parameters that goes. We need a geosynthetic for base stabilization and design method. Then this clearly shows that the soil geosynthetic interaction is a very important parameter in the finite element modeling, for example, here. And that is why we spend a lot of time to talk about that. That's why we said it's important part, because it's really important in ME design. Now, let's finish the presentation by some different scenarios to, let's say, go to, I can call it some examples of what we see and how we should put all this together, let's say. Application one, for example, a stabilization of unbound aggregate. It means we put geogrid. It can be unpaved road or paved road on top of the subgrade or within the granular layer, or it can be railway under the ballast or sub-ballast. The main idea here is the benefits that we want to get here: less deformation and rotting, increase the modulus of the aggregate, minimizing the decrease in the modulus, so we keep the modulus constant during the time, we don't lose the modulus. Traffic benefit ratio, base cost reduction, these are some of the objectives or benefits that we can get. The function, which is determining and where main function is the stabilization or stiffening. Mechanism is lateral restraint is the main one. Properties, we will see in future slides. And some of the performance criteria that we can consider is less deformation of rotting, for example, higher modulus for reinforced aggregate, TBR, BCR. Based on these criteria, we can select a test and then a model that can measure these criteria based on the mechanism and the function. So this is how we actually summarize the presentation so far: objectives and benefits, functions, mechanisms, properties, and then performance. It's about mechanism. Lateral restraint is the main one for this application, as we discussed before, and it's nicely described here. The properties that can be important in this application can be tensile stiffness at very low elongation. Cyclic modulus, some references has concluded that it can be important. Soil geogrid interaction and soil geogrid composite stiffness, junction and roughness or damage resistance. Application two is when we want to stabilize the subgrade. So we are not talking about the gravel or stabilizing the gravel. We want to stabilize the subgrade. So it means we put the geogrid, it is sometimes the same location, but the objective here is to increase the bearing capacity of subgrade. So we can see the location of geogrid can be the same, but the objective is different. That is the important one, what we want to do. That's why I said the first step to start our study is to see what we want to achieve. Then we can decide and then we can analyze the outcome. The geogrid functions can be reinforcement and stabilization or stiffening. Mechanism and properties, I will tell you about that in future slides. The performance criteria can be less rotting or BCR or TBR. Mechanisms, increased bearing capacity, reinforcement can act depending on the testing condition, and lateral confinement through a stabilization or stiffening can act. So both can be mechanisms in this application. And as you can see in this graph by Dr. Zurenbeck, in the left-hand side, you can see it is like a punching shear and punching failure. On the right-hand side, the deformation and the stresses on the subgrade and geosynthetic is now different. I like this photo very well. It's from a study in 2019. And as you can see that darker area is the base course and lighter area is a subgrade, and in between it was a geogrid. So this shows the direction of the strain in the and forces in the subgrade. And also you can see in the geogrid, these flashes are showing the forces in the geogrid. So it clearly shows what's happening, and it's a very good example of studying these conditions. Another application is one we want to stabilize subgrade is when we want to actually stabilize the subgrade by using by going down. So what does it mean? It means that we are having geogrid in between the subgrade and pavement. So this stabilization, this option, that's why I call option 1. We put geogrid directly on the subgrade. The properties that are important are tensile stiffness, tensile strength, depending on the type of the road. Is it an unpaved road? Is it a walking platform? This can be important. Cyclic modulus sometimes, soil geogrid interaction, and junction and roughness and long-term performance depends. For example, in some guidelines, for example, in German rail guidelines, they talk about long-term performance as well. So it depends on the application. Then subgrade stabilization, another way is to excavate, go down, put geogrid and fill it back. It's exactly like replacement, soil replacement, but we are using geogrid to reduce that soil replacement. So here, we are actually in a different situation. The objective is again to increase the bearing capacity, but application is both subgrade stabilization and unbound gravel stabilization at the same time. So it's actually similar to designing an unpaved road, and very similar to subgrade replacement. We are just reducing the amount of replacement. So the criteria can be improving the subgrade bearing capacity or modulus, less subgrade deformation, reducing the thickness of the subgrade replacement, or traffic benefit ratio. The mechanisms, again, it's a combination of both mechanisms for both applications and both that we saw before. Properties, ultimate tensile capacity can be important depending, not directly, but depending on the performance. It's mainly not directly coming into performance because the geogrid doesn't get elongate to the ultimate capacity, never. Tensile stiffness, cyclic modulus, soil geogrid stiffness and interaction, and junction and roughness and long-term performance can be important. And the last application example is on expansive subgrade. Here, we are talking about a stabilization or a stiffening between the gravel. Now, the objective is to delay and reduce the amount of cracks. Function is a stabilization or a stiffening. Lateral restraint is the main one. That is the main mechanism. And the criteria can be reducing the amount of the cracks or delay in the cracks. And the mechanism, according to Dr. Zornberg, can be providing lateral restraint to the base layer, which minimize the base lateral confinement and actually maintain the homogeneity of the base material, and adding ductility to the base layer. So these are the mechanisms that can help us in this specific application. The properties of geogrid: solid stiffness, soil geogrid composite stiffness, and interaction, junction, and roughness. Now, to summarize the presentation and what we discussed, I like this slide, that's why I repeated here. The steps to prove or study the performance of geogrid is to understand the application that leads to that objective. You saw in some last examples that I gave you, it's important to understand the application. Then what is the function? And then what is the mechanism that is going to be important? Then what are the properties are relevant? And then we select the right test and the right model. And then we should analyze the data, integrated analysis. So we consider all the effective parameters, not only one or two, and then we can apply to the test method. Soil geogrid interaction is a combined effect of geogrid type, rib properties, aperture properties, ratio between aperture size to gravel size, rib stiffness, and soil density. The soil geogrid interaction mechanism with surrounding soil, it's a typo here, can be different for different geogrids. Limitation of each test method should be considered. Is the model able to capture all the effective parameters? We should see. And a test result or model for a specific geogrid and condition may not be directly applicable to all geogrids and conditions unless they are calibrated. And the effect of other parameters, which we didn't discuss here, like separation, filtration, drainage, these are also important, and it needs to be considered in the design because we are talking only here about stabilization and reinforcement. We didn't have time to see the other effects And these separation, filtration, and drainage can change the performance. Thank you very much for your time, and thank you for giving me this opportunity. Hope you enjoyed. And now let's go to some questions. All yours, Yamek. Oh, I don't know. Shall we go through the case study, then question?
Yeah, I would suggest we do the case study so we make sure all the presentations are done and then we get to the questions.
Yeah, I'll stop sharing them.
All right.
Okay.
Amar, floor is yours.
Yes, I'm going to try to share my screen. Share. You can see the screen, slideshow. Can you see that, everyone? Yep. Okay. Thank you, Amir. I just want to say my name's Amir Singh. I'm Business Development Manager with Global Synthetics. Today I'm just going to go through a bit of an introduction on the company and some case studies. Firstly, Global Synthetics is a leading distributor and manufacturer of a wide range of geosynthetic products servicing the Australasia and Pacific region. We're an Australian-owned and managed company. We also, I guess one of the things that puts us against other people, or other manufacturers or companies, is that we provide complementary engineering services and design support on a wide range of geosynthetic applications. We have a combined staff industry experience of over 200 years, and most of our staff are also qualified engineers. We partner with leading manufacturers worldwide, and some of them are like on the screen there, Nawa, ACE, and Propex. Now, in the soft subgrade stabilisation side of things, we have non-woven geotextiles for separation, filtration, and some drainage. We have circular-grid polypropylene geogrids and combi-grid polypropylene geocomposites for roads, paved roads, I should say, unpaved roads, rail, wind farm, solar farm access roads. In the soil reinforcement area, we have ACigs high-strength woven geotextiles, ACegrid flexible polyester geogrids, and SecuGrid stiff polyester geogrids. These are long-term reinforcement for embankments, slopes, retaining walls, piggyback landfills, and construction on tailing dams. In the next one, we have ashore reinforcement as well. So we have the ProGrid polyester or glass fibre geogrids. We have our ProGrid Compo PET or glass fibre geogrid composites. These are used for the retardation or reflector cracking on asphalt concrete roads, in airport runways and pavements. In the erosion control area, we have landlock and Puramat turf reinforcement mats. These are sustainable solutions. They provide permanent erosion control. Very good replacement for rock and concrete. They're used on slopes and channels. When you incorporate an anchoring system, we have the Armamax anchoring system, and that provides erosion control and surface stability. We also have geotextile sand containers for coastal protection. In the drainage and hydraulic area, we have geonets. We have wick drains for accelerated consolidation, dewatering tubes, and drain tube blanket drains to, I guess, replace the traditional or traditional, I should say, drainage rock layers. In barriers, we have geosynthetic clay liners and geomembranes. These are used obviously to separate against contaminated soils, and they can be used on landfills, mining, roads and rail, and sometimes behind retaining walls. And we have many more, and you can visit our website for all the products and various applications. I just want to go through some recent case studies in flow and go with the presentation. In the renewable energy sector, including, I guess, wind farms and solar farms, we provide a lot of geosynthetic solutions for access roads and working platforms like crane pads. One project here is the Darling Point Solar Farm Access Road, $450 million project, sorry, I should say. Location was west of or southwest of New South Wales, and this particular project was dealing with soft soil stabilisation. We supplied about 50,000 metres squared of SecuGrid biaxial geogrid. Project went from 2019 and was open in 2020. The next project I want to talk about is the Pacific Highway soft soil treatment. This was quite a big project with many sections. It was a $4.9 billion package. It's located northern New South Wales between Woolgoolga to Ballina. This incorporated the application for basal reinforcement and soft soil stabilisation. The products used on this particular project we supplied was 650,000 square metres of ACigs high-strength woven geotextile, 3.2 million linear metres of wick train, 2.6 million square metres of geothermal non-woven geotextile. Our project went for like 4 years, completed and opened in 2020. The next project is Warrego Highway Upgrade Program. This was a $635 million project. It had 18 sections, I guess you can say, between Toowoomba and west of Miles in Queensland. It was construction on soft and expansive soils. We used supplied, I guess, more than 300,000 square metres of combi-grid geocomposite at the subgrade level for stabilisation and improving the bearing capacity. And we use SecuGrid geogrid in the middle of the pavement layers for stiffening and stabilisation to, I guess, improve the expansive subgrade behaviours. The project went from, I guess, 2014 to 2019. And last but not least, we have the Eaton Range Peak Downs Highway Realignment Project. This was located in Queensland near Mackay, inland of Mackay, and it was an $189 million project. It's actually the largest reinforced slope in the Southern Hemisphere. It's 780 metres long and 45 metres tall at the highest point. There was a reinforced slope application of 280,000 cubic metres of road embankment construction. Product used on this particular project was 500,000 metres squared or more of ACigs uniaxial geogrid. When project went from 2016 to 2020. And that's the case studies I want to share with you all. So thank you, and I'll pass it back over to you, Amir.
Thank you, Amar. If you
just gotta stop sharing.
Stop share from your end. We go through a couple of questions quickly. We just passed 3 o'clock. So a question about application of geogrid products in seawall maintenance and riverbank maintenance with cyclic tidal wave in combination of soft ground condition. Has there been any examples of that application, Amir?
Yes, it has been used in such application like that. Of course, there are some other considerations that needs to be considered here. I can send you some more information if you email me. Definitely, there's details that I will send you about that. Sure.
Sure. Then there was another question about the pull-out test on geogrids. Can the test be carried out on multi-axial geogrids?
Yes, this pull-out test can be done on any geogrid, and it has been done on all different geogrid types. There's no limitation for the pull-out testing.
That's right. And then the last one is in a landfill application for a capping construction. So the question is if the geogrid layer should be on top of the liner, just below the soil layer, or should it be in the middle of the soil layer, and how important that location is?
That's a good question. It's actually a different application. It's like veneer stabilization, and this is a different design approach. There's the design standard and a standard design procedure for that. Depends on what you want to do. You can put it on top of the liner. You can put it in between. The main reason that we put geogrid and veneer stabilization first is if the soil itself has not enough stability, or you want to reduce the forces on top of your liner. So it depends on what you want to achieve. Again, what you want to achieve is always important. We can send you some information on that, some case studies and some design methods that are available. I will send it to the person who asked the question. Sure.
Perfect. All right, that's what we have time for. Amir, if you want to maybe mention your email address, if people want to contact you directly after this webinar.
Yes, I can share my screen. So this is my email address. Please, if you have any question, feel free to be in touch and we can take care of that for you. And thank you again. Thank you, ACigs and CIOMAC and all the attendees for participating and staying, and hope you enjoyed the presentation.
Yeah, fantastic. That was a great presentation, Amir. Thank you very much for that. And Amar, thanks for being with us. All the audience, thank you for attending this webinar and hope you all enjoyed it. For the next month, we're actually having another forum from the ACigs forum series. The title is going to be on TCR, Technical Committee on Reinforcement. So make sure you follow the notifications, the emails that you will see. The registrations are open and we will see you in September for our forum. Thanks everyone and see you next time.
Thank you.